Next we look at Faraday's laws, which basically connect a little bit of basic physics, that is the current and the flow of electrical charge, with some chemistry calculations, that is moles and amounts, masses of metals and the like. It's the calculation topic of this section of work. Now, Michael Faraday made a couple of observations which seem pretty obvious to us now, but was a profound insight at the time. And whereas we use just a distilled formula and we apply that formula all the time and we don't think too much about it, it's important just to have an idea about how he derived that formula. And two observations that he made. First of all, if you're plating a particular metal, so just say you're electroplating silver, then the mass of silver deposited at the cathode is going to be proportional to the amount of charge which passes through the cell. So mass is proportional to Q, the amount of electrical charge. His second law said that if you want to get 1 mole of a metal, it's going to take a whole number of moles of electrons to do that. And that number of moles depends on the metal. So if we want to plate 1 mole of silver, it's going to take exactly 1 mole of electrons, 96,500 coulombs of charge, exactly 1 mole of electrons. If we want to plate 1 mole of either copper, tin or lead, it's going to take exactly 2 moles of electrons. And if we want to plate 1 mole of chromium, it's going to take exactly 3 moles of electrons. Now you've probably figured out already where those numbers 1, 2 and 3 come from. They're simply the charges on the ions in each case. We know that to reduce 1 mole of copper ions to copper metal, it's going to take 2 moles of electrons. And it was Faraday who made that realisation of what's occurring. Now, basically, we use Faraday's laws simply as a way of converting between amounts of electrons, coulombs of electrons, and moles of chemical. So we know that Avogadro's number tells us the number of particles in a mole, 6.02 times 10 to the 23. Coulomb's constant, 6.24 times 10 to the 18, is the number of electrons in a coulomb. If you divide one by the other, you see that it takes 96,500 coulombs to give you 1 mole of electrons. And that's the essential formula for Faraday's law. That's the one that we'll be using quite extensively to convert between electricity and chemicals, between physics and chemistry. So Q, the amount of charge in coulombs. Number of moles of electrons, always put the E minus in brackets so that you know you're talking about the fact that it's moles of electrons, not moles of something else. And then Faraday's constant, which is always 96,500. It's in your data book, it's easy. In fact, of course, I think that relationship is given in your data book as well, so that's easy. Sometimes they talk about the amount of electric charge in Faradays. Well, 1 Faraday is simply a mole of electrons, i.e. 96,500 coulombs. So we can work out Q using our basic electricity formulas and use Faraday's law to convert it into moles of electrons. Once we've got moles of electrons, then we can do our normal stoichiometry stuff to work out amounts of chemicals. So here's a very basic example of what we do. So here we've got a circumstance where we're given electricity information and we're being asked for chemistry information. So the first thing we're going to need to do is use our electricity information to work out Q, the amount of coulombs. And the formula that we use, Q equals I times T. Again, it's in your data book if you don't remember. So the charge in coulombs is the current measured in amps times the time in seconds. Don't forget to always turn your time into seconds. So in this case, what have we got? We've got 20 amps, we've got 30 minutes, so times it by 60 to get to 1800. And multiply the two together, we'll get 3.6 times 10 to the 4. Now, the number of coulombs is always a really big number. Don't be put off by that. In fact, if it isn't a very big number, you've probably done something wrong. Now we can do the essential Faraday's law bit, which is convert coulombs to moles of electrons. And moles of electrons simply equals coulombs divided by Faraday's constant. So we simply divide 3.6 times 10 to the 4 by 96,500 and we get our moles of electrons. Then once we've got our moles of electrons, it's a simple matter of mole ratios to calculate the amount of chromium. So it's a 3:1 mole ratio. So we want chromium metal, we've got electrons, so want over got is 1/3, that's what we multiply it by. That gives us the moles of chromium. And then simple mass formula will give us the mass. So pause now, do the questions and submit them on Google Classroom, and I'll come back and just do a little bit more work on this topic in a second. One last little bit of calculation stuff. There's an example of just the sorts of trickiness they can put into these questions that require you to be a little bit able to manipulate quantities and stuff. So we're using density here to convert between surface area and thickness to volume, and then turning volume into mass of metal. So we've got an object with a surface area, particular surface area, and we know that there is a certain thickness of metal on that particular surface area. We need to know how much metal that is so that we can plate it for long enough and know how much metal we're going to consume. So first of all, we need to convert surface area and thickness to volume. Now to do that, we need to have the same unit. So we've got thickness in centimetres, we've got surface area in metres squared. So we need to turn metres squared into centimetres squared. Well, we know to go from metres to centimetres, we times it by 100. So if we're going from metres squared to centimetres squared, we'll have to times it by 100 squared. So that gives us 500 centimetres squared. Then volume is surface area times thickness. So you've got the three dimensions multiplied together, gets you volume. So we do that, we get the volume of silver required, 10 centimetres cubed. Then we can use the density. So density is 10.5 grams per centimetres cubed. Now those units, of course, give us the formula. So 10.5 equals grams divided by cubic centimetres. .5 equals, well, the mass we've just calculated to be, sorry, the volume we just calculated to be 10 centimetres cubed, and we simply solve for the mass, and what do we get? 105 grams. Just an extra example of the sorts of little twists they can put in.